Hi guys, welcome back to CVRROCKET. Today in this video we are going to check out LSTM forward and backward propagation. So forward propagation, I'm just going to give some equations, and we will see backward propagation mainly because training happens there and how the neural network learns. So all those we will discuss here. And again, LSTM solves some of the problems which RNN have, like vanishing gradient, exploding gradient thing, and it's widely used majorly because a long short-term memory, as a full name suggests of the LSTM. What happens as an intuitive idea, it can store information like long-term information and short-term information very well. And how it does by using forward gates. These are the gates: output gate, candidate gate, cell state, hidden state, and output obviously will get for the neural network an input gate. So using these things, it tries to what are the information it needs to forget and whatever the information it needs to like propagate throughout the network or propagate within the cell. So all those and many more, those things it does using gates and states. So basically backpropagation in LSTM loss function, we are again using binary cross entropy loss. Just for an example, binary cross entropy loss, and here total loss, L total, is basically this is one cell and we will get output over here if we get input over here, and this is a previous H node if for suppose, and we will get Y out over here, and for every Y out we will calculate the loss. So we will get L1, L2, L3, L4, so on till LT, or LT minus 1 if you will take from 0, if you will take from 1 it will be T. So the total loss will be the summation of all the losses, and we need to calculate, actually for a learning purpose, what we do is in gradient descent, new weights is equal to old weight minus dl by dw times learning rate alpha. So what happens is, like, if you draw a graph and dl over here, dw over here, so what happens is, like, if we have learning curve something like this, and if you have a positive slope, so here it is negative, so we need to subtract from old value to come to gradient descent over here. And if you have negative slope, negative, negative, it will be positive, so we need to add something to come to global minimum, and based on some iteration or epochs we need to do this. So these are the like basic equation of gradient descent, what we do. And here we need to calculate weights. So if you try to like optimize the weight and get the good weights, then only we can say that the model is trained perfectly. So we need to find derivative of loss. So what are the loss that nudge, whatever changes in the loss delta, what we are doing with respect to the weights. So that we need to like substitute that to recalculate the weights. And after some epochs and after seeing like early stopping, using hyperparameter tuning, all those things, we can like stop the model if we have got the optimized results. So that model can be learned perfectly, so that if we give our test example by seeing the validation accuracy and training accuracy, we need to see whether there is overfitting, underfitting. If those things are not there, if the model is trained close to perfectly or perfectly, and also, so we can say on the test example also it can perform well. So for the given input, it will give the output as close possible to the actual result. So actual result is nothing but this one, and the prediction result this one. Based on that, because in actual result is like supervised only, so where the data like class labels are available, so that we can calculate the loss something like this instead of using clustering or any another unsupervised learning methods. So here we need to calculate derivative with respect to weights to calculate this, so that we can get the new weights, so that training happens. And here we have UI, input, forgot, output, and here we have gate itself, UG, and here we have input, forgot, output, and gate. So we need to find with respect to all this, and again we need to find weights, and we can also find with respect to biases, dl by db here like this, and du this one, yeah. So dw, du we need to find, and all these things and these things we need to find. So to calculate with respect to weights, gradient with respect to rates, we need to calculate gradient with respect to gates and states, because the weights whatever you are forming, actually the result comes from here, states. As you can see, wi is used over in it is again used over here in cell state. So to find the derivative with respect to dit by dwt, or whenever in the chain rule when it comes, we will surely be required of cell states, hidden state, candidate gate, output gates, derivative with respect to those. That we will show, like I will show in the further coming part.